Okay, well, I have 4 o'clock. Jessica, are you ready for me to do my brief introduction?
I'm ready.
All right, well, welcome everybody to the first of the principal lectures for the workshop in geometric topology. This year, our principal speaker is Jessica Purcell. You can find a short biography of her on the website, but I guess for the sake of the recording, let me mention just one or two highlights. Jessica is a Stanford PhD who followed that up with postdoc positions at UT Austin, University of Texas at Austin, and at Oxford. Worked for a while at Brigham Young and now is at Monash in Australia. She's held a number of distinguished grants, and something I didn't learn until after we invited her was that she's currently both an Associate Dean of Research and President-elect of the Australian Mathematical Society. So we are really extra grateful that she was willing to take some of her very busy scheduled time, I'm sure, to present some talks for us. And with that, I'll turn it over to Jessica to tell us about hyperbolic knot theory.
All right, thanks very much. Thank you for the invitation to speak. And it's, as I was saying earlier, it's great to see so many of your friendly names on your Black backgrounds. So thanks very much for coming along. Let me actually switch slides to a more interesting one. My plan for these talks, I should say as well, is giving 3 one-hour talks seemed a little bit daunting. So instead, I'm going to give 9 15-minute talks. At least that's the theory. And followed by a little bit of time in between for questions if you have them. And comments. So each day I'm going to try and make the talks independent from each other, but the 3 talks per day will build upon each other. All right. So my very first of all the talks is going to be kind of a background introductory talk, just to put us all on the same page and highlight some of the problems that I think are interesting in this area. So I'm going to start. This is a picture from a paper of Tate from, I think this one was from 1867 in the Transactions of the Royal Society of Edinburgh. So going way back, Tate was kind of the founder of mathematical knot theory. And he was a physicist, and but he was trying to classify knots. Originally, he thought that all knots were alternating, which is why these knot diagrams here don't have any crossing information on them. But anyway, he wrote in his collected papers in 1898, this quote that I have here over on the right. He wrote, "The subject knot theory is very much more difficult and intricate one than at first sight one is inclined to think, and I feel that I have not succeeded in catching the keynote." More than 100 years later, I don't know that anybody has caught the keynote. I think that knot theory ends up being a lot more broad and deep than anybody expected. And it's touching on all different areas of mathematics, which makes it still very interesting and very fun and cool. All right, so again, just to make sure we're all on the same page, in this talk, a knot is going to be a subset of points in R3 or S3 that's homeomorphic to the circle, or even more generally, I can take K to be inside of a Y, where Y is going to be any compact orientable 3-manifold. Okay, and that'll come up later. The way that you traditionally describe a knot is by a diagram. So this is a 4-regular graph, and at every single vertex, it has over/under crossing information. So you can see, like, here's a vertex here of this graph, of the trefoil, and the slash over the broken one tells you which strand goes over. So it's really described combinatorially, at least classically. And then we say that 2 knots are equivalent if there's an ambient isotopy taking the one to the other. So this is for knots sitting in in S3, but more generally, if your knot is sitting inside of this compact orientable 3-manifold, then you need this ambient isotopy from the one to the other. Or sorry, from Y back to itself, that slides one knot to the other. Okay. All right, so Tate really did most of his work looking at combinatorics of diagrams, but diagrams are not always the best way to study knots. Starting in the early 1900s, for example, Verdinger was looking at the complement of the knot. And this is just the space that is exterior to the knot. I should say I'm sometimes a little bit sloppy about this. The complement, this is, I think of it as S3 minus K. This is an open 3 manifold. And the exterior is S3 minus a tubular neighborhood. This is compact with boundary. It is a torus. And more generally, if you look at links, then S3 minus the neighborhood of a link complement. So this is more circle components. This is multiple torus boundary components. Okay, and an important result from 1989, so it took a very, very long time, a lot of mathematics, before this was proved, is that if the complements of two knots are homeomorphic, then the knots are equivalent. Really, I should say here, if they are orientation preserving homeomorphic, then the knots are equivalent. This doesn't see the mirror image, the Gordon-Lupi theorem. And actually neither does geometry, which is what I'm going to talk about. So we're not going to care about mirror images of knots in this talk. So once you're looking at a 3 manifold, now you can apply 3 manifold tools to this. And one important 3 manifold tool is geometry. So this, again, going to the historically, this really kind of ties back to Thurston's program for geometrization from the late 1970s and early 1980s. And so what Thurston conjectured, and then the final cases were proved by Perlman in around 2002, 2003, I should say, were that any compact orientable 3 manifold can be decomposed. So you cut it along spheres, disks, tori, and annuli into pieces, and each of these pieces will admit one of 8 3-dimensional geometries. Now, 7 of these geometries are pretty well understood. They have fibering, cipher fibered, or fibering by tori, and the 8th, which is also in an appropriate sense the most common, is hyperbolic geometry. So we're going to be doing a lot of hyperbolic geometry in these talks. So again, I'll just put up a definition. This is a quick slide. We'll go through more properties as we need them. But I'm going to say that M is hyperbolic if it admits a metric with constant sectional curvature -1. That's more the geometric definition. I'm more of a topologist than a geometer some days. So equivalently, you say that M is a quotient of hyperbolic 3 space. So this is the universal cover. So if it's hyperbolic, it has universal cover, hyperbolic 3 space, and it's going to be the quotient of that. This deck transformation group is going to be some subgroup of isometries of hyperbolic 3 space. So some properties of hyperbolic 3 space, typically I'll be looking at the upper half space model. So you can think of that as all the points on the complex plane cross R plus here. So this is the positive points or positive t values. And the metric is given by rescaled Euclidean metric. So you take your usual Euclidean metric on the top, and then you rescale by the height. So in particular, if your 2 points in hyperbolic space, say on these lines, and you move them up, then because you rescale by the height, these 2 points would be getting closer and closer together as you go up towards infinity. On the other hand, if you take them down lower and you're moving them down, notice that they're going to be getting further and further away from each other. So they get exponentially far away. And then this picture also shows some of the important things we'll need, which is that the geodesics in hyperbolic space, these are, the geodesics are either vertical lines like so, or semicircles meeting the plane at infinity at right angles. And I should say as well that there is the boundary of hyperbolic 3 space off at infinity is this plane, the complex plane union a single point at infinity. I'm not sure what my pen was doing there. So, okay. Okay, so as part of his geometrization program, Thurston showed in the 1980s that knots in the three sphere have pretty restricted geometry. So it's going to be hyperbolic if and only if it isn't a torus knot or a satellite knot. This is example over here on the left, we have a torus knot. A torus knot is a knot which you can draw on the surface of a torus without adding any crossings. So it just wraps around a torus as some sort of a PQ curve. A satellite knot here in the middle, this is a knot within a knot. So you take a knot and you drill it out, and then you put in this tube that has another knot inside of it. So a satellite knot is going to have an essential torus. And if you remember from the geometrization theorem, you cut along spheres, disks, tori, and annuli. This is one of the tori that you're going to be cutting along, is this dashed line. Okay, so satellite knots decompose into further pieces. And then over here, I've got an example of a hyperbolic knot. And that's everything else that can't be written as a torus knot or a satellite knot. So even more generally, if you don't have a knot in the three sphere, say, you could still apply some of Thurston's work. So his hyperbolization theorem from the 1980s, he proved that a compact orientable three manifold with torus boundary, it will have interior that has a hyperbolic structure if and only if there are no embedded essential surfaces of this form. So no spheres, no disks, no tori, and no annuli. So I've drawn here a couple of examples of knots that have some of these problematic things. So this diagram here is not prime. So in a prime diagram, you can see that there's this curve that meets the diagram exactly twice with crossings on either side. So that's not prime. You can turn this into an essential annulus by thinking of this as a sphere that's meeting the knot twice. So this is an essential meridional annulus. So this one, this does not have a hyperbolic structure. And more generally, you can thicken this up. If you take the tube around the knot over here, that will build a torus. And that's called a swallow-follow torus. That's also a problem. So this is an example with two of these problematic surfaces inside of it. Over here on the right, this is a knot that was described by Goeritz in 1934. And this is, in fact, this is an unknot. So this is equivalent to the unknot, like so, which bounds an essential disk. So when I say equivalent, remember there's an ambient isotopy of S3 that takes this unknot to this other unknot, and the disk will follow along and you'll get an embedded essential disk in that. I don't know what it looks like in this Goeritz knot picture. It probably does something like, loops over here, twists around a bit. So it's not always easy to find these essential surfaces when they exist. But if you can rule them out, then you can prove that knots are hyperbolic. All right, a really important, useful tool in hyperbolic geometry is Mostow-Purcell rigidity. So what Mostow showed for closed manifolds, Purcell generalized to manifolds with finite volume, is that if two hyperbolic three manifolds, sorry, I forgot key hypotheses, hyperbolic three manifolds with finite volume. So if you have two finite volume hyperbolic three manifolds and they have isomorphic fundamental groups, then they are actually isometric. So this means that if there's a hyperbolic structure, it is unique. And then you throw this in with the Gordon-Luecke theorem, which says knots are determined by their complements, and complements have unique geometry. This means that hyperbolic geometry is a complete knot invariant. So two knots will be equivalent if and only if they have the same hyperbolic structure. So this is nice. This is a great way to solve all of knot theory, except in practice, you need to be able to apply this. So it turns out that it's somewhat difficult to read hyperbolic geometry from diagrams in general. Your computer can do it for examples. So Jeffrey Weeks I think in the 1980s, he built a program called Snappy that will take a diagram of a knot and it will turn it into a hyperbolic structure. It'll compute numerically these things. And this program is now maintained by others. So Mark Kuller, Nathan Dunfield, Matthias Gerner, and other people who still work on this. I'll show you a picture in a second. But what So what hyperbolic knot theory does is it wants to look at infinite families of knots, and it looks at lots of different geometric properties and how these relate to other properties of the knots. So we talk about cusp or volumes, geodesics, cusp shapes, etc. Okay, some diagrams work well with geometry is the title of this slide. So this is an alternating knot, this particular these particular family of knots actually seem to work pretty well with the geometry. So what do I mean by that? I mean, you can see some of the diagrammatic properties reflected in the geometry. This is a cusp neighborhood. So these are screenshots from Snappy. Let me actually change my pen color, if I can remember how. Okay. So what are you looking at? Let me just say a little bit about that. So we're looking at we're in hyperbolic 3 space, and when you look at the universal cover of a knot, a tubular neighborhood of the knot is going to be a torus, and this is going to lift to a horoball about infinity, and you'll see the torus will be the cover of that will be on this horoball. So when we're looking at Snappy, our heads is up here, and we're looking down on this pink square here, or pink rectangle that you can see. This is the fundamental domain for the torus that's part of the cusp. Other copies of horoballs, these other circles that you see, these are translates of this original one down to the boundary of infinity. So remember that we have our knot complement is H3 mod gamma, and we have this horoball H. These are images. These are translates of this horoball under gamma. Okay. All right. So now, if we are inside of this diagram, so I'm going to start here. I'm thinking of myself as sitting on this torus, and I'm going to be walking along the torus. And as I walk, I will see bits of knots in terms of crossings flying over myself or under myself, right? So I start here, and I run into this first crossing, and I see, so this crossing says that if I look out into space, I should see another copy of the torus in the distance. And here we go. So I'm going to start on this side of the cusp, and I see this horoball that I'm going to call 1 here. And then I keep walking. So keep walking. I see another crossing, but actually this crossing is isotopic to the first. So I'm not going to see anything new when I go that way. But if I carry on, I'll see another crossing here. So I'll label that guy 2. And then 3. And then 4. 4 is one of these, it's isotopic again. So we have a crossing here. It's isotopic over to here. So as I carry on, I don't see anything new until I get here. Let's call that 5. I'll put a 5 there. And then I come back to 2. And then I come around to 6. And then I'm back at 4. And then I see 1 again on this side of it. And I keep passing through. And then I see a 5. What is that? That's 3 again. A 6 again, and then I am back where I started with a 1. Okay, so for this particular diagram, what have I done? Every single big horoball that I see out in the distance seems to correspond to a crossing in this picture. So this is an observation that first was made by Thistlethwaite in the 1990s. This thing that I've drawn, this is all purely speculative, conjectural. There's no concrete proofs of anything mathematics here. So this is a conjecture that Thistlethwaite was making in some talks in the 1990s, early 2000s. His conjecture is that crossing arcs in alternating knots are always short. So in other words, if you take any alternating knot and you follow the diagram around, then you'll see this pattern for all alternating knots. Okay, so I think, this is pretty cool. This is pretty fun. Those of you who are new to hyperbolic knot theory will be really excited to get going and try all of your favorite knots. Not all knots work well, though, with hyperbolic geometry. So these are examples of knots that are built with small numbers of tetrahedra. And they have, even though they've got lots and lots of crossings, these crossings don't seem to have the same patterns that the last one did. So for example, this is the -237 Purcell knot. It can be built out of exactly 3 tetrahedra. If you give this to Snappy, it'll give you a picture that looks like this one on the top here. And you'll see these pink lines going off to the edges of the screen, and you'll try and zoom out as far as you can, and they'll still go off to the edges of the screen. These are the standard meridian and longitudes, and they are they're very, very long and skinny. They don't fit on the screen. But if you switch, you can get Snappy to make the torus generators the shortest curves, and then you get something like this. But you can see here, there are like 3 horoballs. I don't know, maybe that one is separate as well. But lots and lots and lots of crossings here in this diagram. Okay, so it's not quite as clear what's going on from the diagram on the geometry here. So lots of open questions in hyperbolic knot theory. Okay, that's the end of my first talk. So let me pause there for questions. Are there questions? Maybe as I pause for questions, let me show you the cool picture.
I'll ask a question.
Okay, great, thanks.
In one of your previous slides, you had a snake wrapped around, was that a pea?
Yeah, Snappy, yes.
What's the snake? The significance of this?
It's a play on. So this is a play on the program. The snake. It's based on the fact that they took Jeff Weeks' program, which he called Snappy, and they put it into Python language.
I see.
Yeah, that's where that came from. Yeah.
Other
questions?
May I ask, what is satellite? Not exactly.
What is a satellite knot exactly? Yeah, a satellite knot is a knot. Well, it has 2 pieces. It's got a companion and a pattern. So the pattern is sitting inside of, it's a knot within a solid torus, blah, blah, blah. And then you take the solid torus and you embed it in the neighborhood of another knot. So it's a knot within a knot.
Which one of them is satellite?
This knot, so this black thing is the satellite.
Okay, thank you.
Yeah. Okay, other questions?
So in practice, yes. Sorry. Can I?
Go ahead.
Thanks. So since you're already on this slide, so for those satellite nodes and those torus nodes, how easy is it to recognize if your knot is one of those?
That's a good question. It's pretty difficult, honestly. It's hard. If somebody throws you a random knot, there are some tools that can do it. So you can, for example, you can feed it to the computer. It can triangulate it. Ben Burton has a program called Regina that will look for essential surfaces, and so it can identify essential tori, but it takes some time. It takes a long time. So in general, it's not an easy problem to find these things. It can take a lot of time, compute time. Yeah.
Thanks.
So I was wondering about the following. I'm sorry, I will not be able to precisely pose the question. So I heard that Snappy can very often compute triangulations that carry the hyperbolic geometry of the corresponding knot complement, but there is some conjecture or that it is not fully proven that these triangulations always exist. So yeah, I'm mumbling something, but could you please elaborate on this? Or
yeah.
I don't remember exactly.
So Snappy solves a nonlinear equation to find a hyperbolic structure, and when it was originally created, it was not rigorous. So there are some tweaks to it that can make it rigorous, but the caveat that, so you can prove if Snappy gives you a hyperbolic structure, you can do a little extra work and you can have it, and you can get a proof that you do have a hyperbolic structure. But this will only work. So first of all, it has to find you a hyperbolic structure. Secondly, it needs to be able to guarantee that the tetrahedra, so it'll triangulate this into tetrahedra, it needs those tetrahedra to be positively oriented. And so if it can find a positively oriented structure, it can guarantee, yes, you have a hyperbolic structure here, everything works out. But it can't always do that. So for example, I have a project where we run lots of triangulations of 3 manifolds, and we can't always find a positively oriented triangulation. You can do some randomization to get new ones, and sometimes we can find something there, but it's not always guaranteed. So yeah, so Snappy is not always, it's not guaranteed. If you find something you like, then you can sometimes use that to prove that you have what you think you have, but not always. Yeah.
Thanks a lot.
Yeah, so the computer, again, it's a great tool along the way of proving something more interesting, but it's not always a perfect tool. Okay, so maybe I'll move on to my next part of my talk. So the next part is about alternating knots. Alternating knots work really well with hyperbolic geometry, and I'm going to spend the next little talk telling you some reasons why. So what is an alternating knot? I should say, by the way, this is a knot where if you walk along the diagram, the crossings alternate from over to under. So over, under, and then you keep going, over, under, over, under. I'm not going to go all the way around this one, but this is a random knot with 25 crossings. I think you can ask Snappy to give you such a thing. To Nathan Dunhill has written a problem to do this, or a program. The diagrams of alternating knots, they seem to encode hyperbolic geometric properties more than other families. And so I showed you this other picture where you could see these big horoballs. These seem to be key in alternating knots. So here's some examples of some results that have been proven for alternating knots. And this is only a snapshot, but these are some famous results. So in the 1980s, Bill Monash he determined exactly when alternating knots are hyperbolic. In the 2000s, Mark Lackenby was able to bound their volumes above and below in terms of properties of the diagram. People are also looking at their exceptional Dane fillings. This is where if you take the knot and you plug in a solid torus, then you'll get something out. Thurston showed that most of these will be hyperbolic, but not all. And so the question is which ones are not. That's what an exceptional Dane filling is. And we'll say more about that in other talks later. But just briefly, in the 1990s, Monasco and Thistlethwaite found some conditions on their exceptional Dane fillings. Lackenby found more in the 2000s. And then a really geometric result is Colin Adams in 2000s, and then some follow-up work with myself and Dave Feeder and Kalfagianni. We found when the checkerboard surfaces of these have this property, this geometric property called quasi-Fuchsian. Okay, so I'm just going to kind of say that briefly, but you can see there's lots of information here on geometry of alternating knots. So a good question is, what is it about these knots that makes them work well with the geometry? And we would like to be able to generalize this as much as we can. So these properties, the combinatorics of the diagram seem to be working well with the topology, seem to be working well with the geometry, and it'd be nice to say more. So if you look at these results, the proofs of these things carefully, then secretly, they are all really results about surfaces. So if you go back, so for example, Monasco's result from when he classified which of the alternating knots are hyperbolic, he was using Thurston's hyperbolization theorem that I put up earlier. So a compact orientable 3-manifold with torus boundary, it has interior with a hyperbolic structure if and only if there are no spheres, disks, tori, and annuli. So what Monasco did is he went and looked at how would spheres, disks, tori, and annuli interact with the combinatorics of a knot diagram. And using this, he was able to control such surfaces and basically to rule them out. Okay, so I'm going to go through, I'm not going to tell you the way that Monasco proved this. I'm going to go through more of Lackenby's tools. on how you get these surfaces, but I should say that the proofs are very, very closely related for a few of these results here that I listed. And you can use similar techniques to get all of them. So I'll just go through one particular construction, which is a checkerboard decomposition. So starting with a diagram of an alternating knot, we're going to decompose this into pieces that have nice topological properties, combinatorial properties that relate well with the diagram, and they're going to give us information about surfaces within the knot and about the way that they relate with the combinatorics. Okay, so the way that you think about this decomposition is you've got this knot is sitting on a projective surface, so a sphere, S2, sitting inside the 3 sphere. And on one side of it, on the top, there's a ball, on the bottom, there's a ball, and you think of this ball as balloons. I think it was Thurston who originally saw this picture, but then you start expanding the balloons. So as you expand the balloon on the top and you expand the balloon on the bottom, then they're going to start bumping into the regions of the diagram. So let me change my pen again. So, right, so the balls are going to start bumping into each other in these little regions, and these are going to become faces of two polyhedra that I'm going to obtain from the top and the bottom. Okay, so how do these faces interact? Well, you expand the ball, you've got the 2 balls are meeting on a region that looks like this, and they're meeting until you come to an edge. And then when you come to an edge, or sorry, when you come to a crossing, these things will bump into each other. So over here in this diagram, we've got the region coming from the left meets the region coming from the right at this crossing. So at the crossing, we have these things that are called crossing arcs. Okay. And depending on where your head is, you will see this crossing arc slightly differently. So if my head is on the top and I'm looking down, then I'm going to see this overstrand. So this is with my head on the top. I'm going to see the overstrand of the knot like so. It's going to bump into another crossing arc over here, another crossing arc over here. And then I'm going to see on one side, I'll see this arc labeled 2, splitting these 2 regions apart. On the other side, the same arc labeled 2 is going to be splitting these other 2 regions apart. Okay. On the other hand, if my head is underneath and I am looking up that way, then I will see a different picture, because what looked like from the top, I see these overstrands. From the bottom, I will see the understrands. And so from the bottom, I'm going to see this understrand instead of an overstrand. And then these 2, the crossing edges labeled 2 are going to be separating basically this face from this face instead. Okay. And then similarly for these other 2. So it kind of flips like this. All right, so that's the decomposition into faces and edges. We need vertices. What do you do with the vertices? You have these knot remnants. Remember, we're looking at the knot complement. So the knot is really not part of the picture, so we just shrink it away. So when I take this picture here and I collapse, so this is the bottom picture, if I collapse all of this tube thingy to a single vertex, I get this over here. So this is what you get on the bottom, and this is what you get on the top. And you'll notice that each of the vertices will be 4-valent, and you'll get something checkerboard colored. And in fact, it's going to look a lot like your original knot diagram. So I've worked through this quickly for the figure-8 knot complement. If you do this expansion for the figure-8 knot complement, you'll have these checkerboard coloring. You'll be putting in, from the top, you're going to put in edges like so. This is the top, this is the bottom. And then when you shrink the bits of overstrands or understrands to ideal vertices, you get these 2, these are combinatorial polyhedra now. So this is supposed to indicate we have a ball on the top, we have a ball on the bottom, and we have these faces given by the blue and the red things, and we have the edges given by the purple things labeled 1, 2, 3, 4. And then we have the ideal vertices. So the result is two polyhedra. Each of these polyhedra has the combinatorics of the original diagram. So you've got four valent vertices. You have edges that now correspond to diagram edges, and faces correspond to diagram faces. And you can see that you can get from the top to the bottom, you do this thing that Thurston called a gear rotation, which is your, in the blue faces, you rotate everything by one. So the one here is over, the one on the top is here. It's been rotated by one in the anti-clockwise direction. In this face, similarly, the three here gets rotated this way. Whereas if you're in one of the red faces, you rotate exactly opposite. Okay, so you have this, the blues rotate one way, the reds rotate another. And when you do this rotation and you glue, you get back your knot complement. Okay, so this is great. This means that when we are looking at the way that surfaces intersect the knot complement, we can actually think about the way that surfaces intersect two polyhedra, and the polyhedra have the combinatorics of the knot complement. Okay, take your essential surface and you put them into what is called normal form. So the normal form for polyhedron, we're going to isotope all the surfaces to meet the checkerboard polyhedron. You can do it so that they meet it in disks. And these disks will be in normal form if they meet everything, they meet all the faces, edges, and these and truncated vertices. Sorry, I should say we're going to truncate the vertices rather than they're ideal. They don't exist. It's hard to deal with things that don't exist. So just truncate them to get something compact. And then if you have a surface that's embedded in this, make sure that it intersects everything transversely. And then the further things that you can do, you can isotope your surface so that these disks of your surface, they don't intersect the boundary in a single face. You don't have arcs running from one side back to the other, and no arcs from a truncated vertex back to itself. Let me try and illustrate that a little bit on this picture. So these red arcs are supposed to be indicating bits of surface that are problematic. So remember, so they're polyhedra here, and the surface is extending into the polyhedra. So if you have this boundary of a surface on the polyhedron, it goes through an edge and then it immediately turns around and goes right back. You can see this is inefficient, right? This is a stupid way to put your surface. We can just isotope this way and we can remove that. So if you have a bit of arc that goes like this is a contradiction to number 3. And you can see that you can just slide it through and get rid of that. Okay. Similarly up here, this one breaks number 4. And again, you can just slide through this disc and you'll remove at one of the intersections here. Number 2 is shown here. This is a little bit different. But if you have a surface that's meeting one of these faces in a disc, now you have to use the fact that if this disc is essential, sorry, the surface is essential, it means that there must be some other disc out here that's contained in the surface. And then you have a disc on your surface, you have a disc on your polyhedron, you have a disc on your surface. Together they bound a ball. You can use that ball and you can slide through. This is using, well, some irreducibility here, I guess. If it's not irreducible, you can cut and find a ball or a sphere that still has this property. Okay, so normal form. So we're going to put all of our surfaces into normal form with respect to these polyhedra, and it's going to have these 4 properties. The tool that Mark Lackenby introduced was this idea of combinatorial area. I think it was Mark at least. So if you have a normal disk inside of your polyhedron, then every time this boundary of the disk hits an edge, so boundary of disk meets an edge, you add angle pi half onto that. So you think of all of these edges as being right angles, and when your disk runs around them, it picks up a right angle. And then after you take the total sum, you subtract 2 pi. This is related to the fact that this is a disk. And then if you take your whole surface and you put it into normal form, then you'll have all of these normal disks, and you just sum up the areas of these disks, these combinatorial areas of the disk, these numbers of times that it hits the edges, and that gives you the total combinatorial area. And then an important result is that if you have a prime diagram, so remember a prime diagram, you can't have a curve meeting if the curve meets the diagram twice, then it has to have no crossings on one side. So this is not a prime diagram. When the diagram is prime, then the combinatorial area of each disk will be positive, or sorry, will be non-negative, so that the whole thing will be non-negative. All right, well, so that's just combinatorial and not very inspired. The inspiration comes from the fact that in fact, the combinatorial area, because of the way it was built, it satisfies the Gauss-Bonnet theorem. So your combinatorial area of your surface, that should be a capital S, this is equal to -2 pi times the Euler characteristic. And so then immediately, just after introducing these definitions and these results, you can see that there are going to be no essential spheres or disks in the complement of this thing. I give the proof. So proof, if you have an essential sphere, then the combinatorial area of a sphere by the Gauss-Bonnet theorem is equal to -2 pi times the Euler characteristic. Okay, but on the other hand, we know that the combinatorial area of any surface has to be greater than or equal to 0, and so that's a contradiction. Because this is built of these normal disks, they all have area greater than 0, you can't get negative Euler characteristic. And that's it. Remember, so for the spheres, disks, tori, and annuli, we're looking for things that are hyperbolic. You can analyze the combinatorics of normal disks that have combinatorial area 0. And that will give you the fact that basically in order to have essential annuli, you need these, you're going to need strings of bigons, basically. And that allowed Monash to classify when these are hyperbolic. So what he showed is if you have a non-split alternating link, which is not a torus link, sorry, non-split prime alternating link, not a torus link, then its complement is a complete hyperbolic structure. And the proof is that in this case, you can show just using these combinatorial arguments that there are no embedded essential spheres, disks, tori, or annuli, and then you apply Thurston's hyperbolization theorem. There are torus links that are alternating. These are the 2Q torus links. They look like this. So these are the only prime alternating links that are not hyperbolic, are these 2Q torus links, but no satellite ones. Okay, that's the end of part 2. So let me pause for a second for questions.
Excuse me, Jessica. Can you say something that, like, how can we say that this there will be no essential tori and annuli?
Yeah, I swept it into this one slide. It's a little bit more complicated. So you need to look at essential tori and annuli. These would have combinatorial area 0. And so then you need to say which of your normal disks might have area 0. So if you go back to the definition of combinatorial area, these are going to be the disks that meet exactly 4 edges. And so in this picture here, I've got an example here of a disk that's meeting exactly 4 edges. It's got 2 edges coming from the diagram, 2 edges coming from a boundary. And then you play with this gear rotation, and you can see how these things glue together, and you use the fact that it's prime, and you can build things like this is going to be translated into a string of bigons. So that's it takes some work, but that's my short summary. It's combinatorics of the diagram, basically. You can follow it along. Yeah.
Thank you.
Other questions?
What breaks if the knot is not alternating?
What breaks if the knot is not alternating? That is also a good question. It's this decomposition won't be as nice. So you can still do this whole decomposition. You can expand the balloons. You'll get things meeting at crossing arcs. The trick is, though, here, my crossing arc, just one overstrand is bounded by these 2 edges that on the, the 1 and the 3 here. If it's not alternating, then you may have multiple strands running through. And so your overstrand will look like you'll have a big blob, and then you'll have a bunch of of edges coming in. And when you collapse this, you've got this really high valent vertex, and it doesn't have anything to do with the combinatorics of the original diagram anymore. So you can't use the combinatorics that you originally had to trace through some of these same arguments.
I see, thanks.
Yeah. Yeah, so it's kind of very special, I guess, basically, the very nice for the alternating case. All right, well, maybe I'll move on to the last sub-talk. And this is about, so these weakly generalized alternating links. This is work that I've done with Josh Howie, and also some with Effie Kalfagianni and Anastasia Tsvietkova. Alternating links have nice hyperbolic geometry. We can read it from the diagram. We can look at volume bounds, but unfortunately, most knots are not alternating. So I think it's Thistlethwaite proved that as the number of crossings goes to infinity, the proportion of alternating knots goes to 0 out of all if you enumerate knots by crossing number. So one thing that we can think about is we can generalize the projection surface. Classically, you put diagrams on the 2-sphere sitting inside of the 3-sphere, but you can also project to other surfaces. So for example, Colin Adams had a paper in 1994 where he looked at toroidally alternating links, knots that are alternating on a torus, on a Haygarth torus in particular. And so every single knot is going to have a diagram that will be alternating on some sort of a projection surface. This is a fact. And so the thought is, what of these techniques can we push? Another way that we can generalize things is we don't have to look at knots in the 3-sphere. So classically, everything is in the 3-sphere, but in modern applications, we're seeing more and more knots that are arising in different places. So virtual knots, for example, they live on a thickened surface. I was just at a really early morning talk on if you take geodesics in the surface, then they live to a unit tangent bundle, right? So this is, so lots of interesting things happening in other manifolds. So then the question is, which of these tools can we generalize? So let's go back through this last talk and see what will still hold. So before we had these 3-ball balloons that we expanded to get this checkerboard decomposition. So more generally, we're now in some sort of a 3-manifold Y, and we've got a link sitting on some of a projection surface. I don't know what I've called it later. Let's call it P for now. But if you take the Y minus P, then it's going to have these pieces, and you can expand these pieces of Y minus P just as you did before. There's no reason your balloons have to be spheres. You can have toroidal balloons, you can have whatever balloons you want. Okay, so you can still do this. Okay, so now how would things meet? So you'd still have these faces that are regions of the diagram, and they're still going to be meeting at crossings. And so everything basically will go through locally on this new projection surface. So you get this thing that we called a chunk decomposition. And because it is alternating, so this goes back to that question that we just got at the end of the last talk, because it's alternating, you're going to have this really nice diagrammatic property. So you'll get this, you'll chop your manifold into pieces. These pieces will depend on your projection surface, on whether it's separating, but you'll have on these new boundary components of your 3-manifold, you're going to have this projection surface labeled with this 4-valent diagram graph, and you'll have the same gear rotations that you had before. Okay, so all of this is okay, as long as you're happy with non-ball balloons. All right, the next step of the program was to see how the surfaces met these polyhedra. So now we've got these chunks. So we're going to have to, we want to put surfaces into normal form again, and we have to change things up a little bit. So we're going to say that a surface in a chunk is going to be in normal form if, so number 1 is the same. We still need to meet our faces, edges, and truncated versus vertices transversely, we still don't want a boundary component to bound a disk in a face. So before we just said we don't want any closed curves in a face. We still don't. We don't want something that we can push off. Remember, by the incompressibility, this would bound a ball and then we could push it through. But you have to say this, you need to make sure that you say bounding a disk, because you can now have curves in non-simply connected faces. So like this curve right here that runs in an annular face, it doesn't bound a disk. It's perfectly fine for my surface to intersect the face like that. Okay, but then everything else is basically the same. So you don't want something like that. You would push it through. You don't want things to chop off corners. You would push it through. And then finally, the last thing that we need is that the surface inside a chunk has to be incompressible within the chunk. So not just incompressible more broadly, but incompressible within the chunk. And you can show that you can isotope incompressible surfaces to have this property. Okay. All right, then again, we can generalize this idea of combinatorial area. So if we have a normal surface within a chunk, we can define a combinatorial area by looking at the edges met not by S, but really by the boundary of S is what I mean. Every time you hit an edge, you get this, you think of that as a right angle, you add pi half to your count, but then you need to subtract off the 2 pi times the Euler characteristic. So before, when we were looking at disks, this was always +1, but now we're going to be subtracting off possibly some negative things or 0 things. And we define the total combinatorial area to be the sum of, that should be the sum of the area of SI. So when you intersect your surface with this chunk decomposition, you put everything into normal form, you're going to have these normal pieces in a chunk building the entire thing. The total area is just the sum. And then again, the same steps of the proof we'll go through to show that you have the Gauss-Bonnet theorem in this case. All right. Okay. When we were looking at alternating knots, we proved that these things had no spheres or disks by saying the area has to be non-negative, but the Euler characteristic would give you something negative over here. We need to be able to say things about positivity again of combinatorial area. So we're going to have to look at disks meeting the knot. We want to ensure that the area is non-negative to use the same tools. And so again, we need this notion, we need some notion of primeness. But so this is something that Josh Howie actually defined. Weakly prime, if you have a disk on your projection surface, so now this surface can be something besides a sphere, the disk needs to meet, if your disk meets the diagram twice, then it has to have no crossings in between. So this is an example of something that is not weakly prime. And then the other thing you need to worry about are compression disks. So I didn't say, this is really super general. You can have surfaces that are compressible or incompressible as your projection surfaces. If you happen to pick something that is compressible, then you're going to get compression disks and you need them to meet the knot nicely as well. So if you have a compression disk that meets the knot 2 times, again, that's going to give you a problem for your this negativity thing. So what Josh defined was the representativity of a diagram. And this representativity, it counts the number of times that a compression disk meets the diagram. And we're going to require representativity at least 4 for our purposes. Okay, so once you have these 2 conditions, if it's weakly prime, if the representativity is at least 4, then the combinatorial area is always non-negative. So then it immediately follows from this. So this is a result that's in a paper of mine with Josh Howie, 2020. If you have a diagram that's alternating on a generalized projection surface, weakly prime, representativity at least 4, then there are no embedded spheres or disks in the complement, and the proof is just the same as it was in the alternating case. Okay. All right, so let me skim ahead. So in interest of time, we have some further geometric results. our main result is, again, if we have a weakly prime, we have this knot that's alternating weakly prime representativity at least 4, and some conditions on the ambient 3 manifold, then we are able to prove when the diagram is hyperbolic. We're able to generalize this result on quasi-Fuchsian surfaces. We get lower bounds on the volume, and we also can get results on the exceptional Dane fillings. And this was work with Josh. My colleague Effie Kalfagianni came to me and said, "You've got a lower volume bound there, but what about an upper volume bound?" So traditionally, upper volume bounds are actually a lot easier than lower volume bounds. So for example, if you look at Lackenby's paper on volume bounds of alternating knots, his proof that there's an upper bound on volume is only 2 pages, whereas his proof for the lower bound is 13 pages. So Josh and I had a lower bound, so surely we ought to be able to get an easy upper bound for these weakly generalized alternating knots. But after thinking about it for a while, we realized that actually this is going to depend on the 3 manifold. Sometimes we'll have them and sometimes we will not, depending on where we are, the 3 manifold is embedded. So to state my results, the results are in terms of this thing that's called a twist number of a diagram. So a twist region on a diagram is where 2 strands twist around each other maximally. And if you have a box like this thing D with crossings on either side, you can flipe that. You can put all of the crossings on one side or the other. So that you say a diagram is twist reduced if you've done all of this fliping and all of your strings of crossings are all grouped together. And in that case, then you count the twist number is the number of twist regions in this reduced diagram. Okay, so Effie and I were able to show that for virtual knots, we have upper bounds always. So for virtual knots on a torus, you get upper bounds in terms of the twist number. For a higher genus surface, you have a different upper bound. And then the lower bounds were the ones that Josh and I came up with. These are also in terms of twist number. So the volume is roughly, it's proportional to the twist number linearly. On the other hand, we found a family with of knots in S3 that lie on a Heegard surface of genus 2. The volume goes to infinity, but the twist number is fixed. So there is no upper volume bound in this case. Okay, and then let me skim through. It's constructive. We build these examples, but let me leave you at the end of this first talk with just some open questions that are related to this. So big question, what is it about this 3 manifold and surface combination that gives these upper volume bounds? In our particular case, when we had a compressible surface, we got no upper bound. When we had an incompressible surface, we found upper bounds. And so question to think about is, can this generalize? Can you always show that if there's some sort of a compression disk, can you rule out a volume bound versus incompressible? Can you always find a volume bound? All right, so let me stop there. Thank you.
All right, let's all thank Jessica. Not just 1, but 3 talks all in one day. So for what's coming up next,